Hello everyone, in this video I'm going to show you how to find the domain of some different functions. So let's just jump right into it. So there are two things you need to look out for when you're trying to find the domain of function. One, if there are any variables in the denominator. So for example, like a rational function. If you see a variable in the denominator, you have to make sure that the denominator is not zero. And two, if you have an even root in your function. If that's the case, you have to make sure that the inside of the even root, what's underneath the root, the radical symbol, is greater than or equal to zero, but we also call it the radicand. If you don't have either one of these two cases, then you don't have any restrictions in your domain. It's just all real numbers. So again, the domain, you can think of the domain as what real numbers am I allowed to put into the functions so that I can get out, so that my output is another real number. So you want to know, again, what real numbers can you put into the functions, evaluate those functions at those numbers so that the output is another real number. So in this case, if we put a number into the function that makes our denominator zero, that's where the function is undefined. So we don't get a real number out. And here, if we put a number in that is less than zero, then we're going to be taking, for example, the square root of a negative number, like the square root of -4 is 2i, which is an imaginary number. So neither one of these cases will give us a result of another real number. So let's look at some examples. So here we have our first function, and we see that we do not have, this is not a rational expression, it doesn't look like a fraction, there's no variable in the denominator, and there is no even root, right? There's no square roots or fourth roots or anything. So our domain is just all real numbers. Okay, pretty easy. Here is an example where we have a variable in the denominator. So as I said earlier, we have to make sure that the denominator is not equal to zero. And I just write it like this and then go about my rules for solving for x. So let's go ahead and do that. We have a difference of two squares. So it's a quadratic. So we need to write two sets of parentheses. So it's plus 2 minus 2. And then we take one factor that can't be equal to 0 and the other factor that can't be equal to 0. So we have x can't be -2 or x can't be 2. So for the domain of this function, we can input any numbers into here except for -2 and 2, because -2 and 2 will make the function, that's where it's undefined. -2 squared is 4, 4 minus 4 is 0. -2 and 2 make the denominator 0. And of course, we do not have to worry about the numerator. It doesn't matter what's going on here in the numerator. So what I like to do is I like to draw a picture of this on a number line and then write it in interval notation. So I'm going to do it on this side. So we can't have -2 and 2. So I'm going to denote that by open circles. That can't be part of our answer. But all of these numbers can be. Everything else can be. So I'm going to write that in interval notation. So we have, reading left to right, what we shaded, -infinity to -2. So -infinity to -2. And we can't include -2. So I denote that here with the parentheses. And of course, infinities always have parentheses on them. Union, -2 to 2. And then another union, 2 to infinity. See if I can write that all on one line. I'll write that here across. So -infinity, -2, union, -2 to 2, union 2 to infinity. So there's your answer. Again, we read left to right what we shaded, and we're not including negative 2 and 2, so we denote that here with parentheses. Okay, so in this next function, again, we have some variables in the denominator. So we take our denominator and set it not equal to 0. And then I just go about solving for x. It's a quadratic. So I write two sets of binomials and two numbers that multiply to be positive 2 is positive 2 and positive 1. And at the same time, these numbers add to be our b term. So 2 plus 1 is 3. And then we set each factor equal to 0. So x plus 2 equals 0 or x plus 1 equals 0 does not equal 0. Just to emphasize that, these cannot be part of our answer. They can't be in the domain. So x can't be negative 2. X can't be negative 1. So again, I like to just put them on a number line. So we have negative 2, negative 1, and we can't have these as part of our answers, right? Because these numbers make the denominator 0. And so that's where it's undefined. But it can be all of these numbers. So reading left to right on the number line, we shaded from negative infinity to negative 2, union, and then in here, negative 2 to negative 1, union over here, negative 1 to infinity. Okay. So moving along. All right, so here we have an even root. So what we do in that case is we take the inside, which is the radicand, and make sure it's greater than or equal to 0. And we just solve for x. So if 3x is greater than or equal to 12, divide both sides by 3, x is greater than or equal to 4. So if you draw that on the number line, so we have 4 all the way to infinity shaded, and I denote that I'm including 4 because here this equal to means I'm including 4, so the bracket on the number line means I'm including 4. And then I just read left to right where I shaded, and I start from 4, and I include 4, so I'll put a bracket there. And then infinity. Infinity always has parentheses. Okay. So then I look here at this function. Well, I have two things going on. I have an even root in the denominator and a variable in the denominator. So with an even root, we know that the inside has to be greater than or equal to 0. But we don't want it equal to 0 because it's in the denominator. So when you have an even root in the denominator, you just take the inside, or the radicand, as we call it, and just make it greater than 0. And then solve for x. So we have 2 is greater than x. So x is less than 2. So here's 2. And x is less than 2 is what's makes up our domain. So reading left to right, we go from negative infinity, comma, 2. And that's it, written in interval notation. Okay, so here's another one of the same kind. So we have an even root and a variable in the denominator. So we take the expression under the root and set it greater than 0, right? Because expression under the root can be greater than or equal to 0, but it's in the denominator as well. So we don't want it equal to 0, but just greater than 0. So we have x is less than 4 this way. So reading left to right, we have negative infinity to 4 as our domain. Okay, in this function, we have an even root and we have a variable in the denominator. So we have to watch out for two things. So the first thing is the even root. So we have to make sure that x squared plus 1 is greater than or equal to 0. Now, this expression here is always going to be greater than or equal to 0 because we're going to square a number and then add 1 to it. So it's always going to be greater than or equal to 0. And if we try to solve, another way you can see it is if you try to solve for x here, you would get imaginary solutions. So we can't solve for x. So we know that there are no restrictions here. We can put any number in here and we'll always be able to take the square root of it. We're never going to have to take the square root of a negative in this case. And then you have to watch out for the x, this case. The denominator can't be 0. So x can't be 0. So here we can have anything, right? Here it can't be 0. It can't be this, but it can be all this. So your answer is where you shaded twice. So from negative infinity to 0, union 0 to infinity. Oh, that's how I like to look at it. When I have two things to watch out for, I just look at the intersection where I shaded twice. Okay, so here we have an even root, and we have to make sure the expression underneath the even root is greater than or equal to 0, so we solve for x. Divide both sides by -1 to finish solving for x. Now, when you divide or multiply by a negative number in an equality, you change the direction of the arrow. So we get x is less than or equal to -2. And if we draw a picture of that, here's negative, see, here's -2. And it's just less than or equal to. So we can use a closed circle or a bracket. So on the interval notation, we'll put a bracket. You can either put a bracket or a closed circle on the graph, and you don't even need to do the graph. But that would be the answer in interval notation. So this is your answer here, and this is your answer for this one. Okay, well that is all I have. So again, when you are trying to find the domain of a function, you're trying to find the real numbers that you can input into the function that will allow you to get out another real number. So there's two things that could happen that won't do that. If we have a variable in the denominator, right, numbers that make the denominator 0, we don't want that. Right, we have to throw those out. So we have to make sure that if we have variables in the denominator is not 0. And so we throw those numbers out. And the other restriction is if we have any even roots. Okay, with even roots, you have to make sure the expression underneath the root is greater than or equal to 0. Because if we were to take the square root or fourth root, or any even root of a negative number, that will give us back an imaginary number, and we don't want that. So we need to throw those out. And that is it. Okay. Well, I really hope that helped. Please feel free to check out my other videos. I have many other videos over tons of other topics. And I will talk to you on the next video. Thanks, guys. Bye.